So we'll have a nice small group for today, which means we should have plenty of times for questions, answers, and talking about different ways we can actually apply some of the things we'll be talking about today. So thank you for coming to my talk about what CRDTs, distributed editing, and the speed of light means to your writer friends. So hopefully that intrigues you a little bit and might motivate you as we get through the rest of this talk. So a little bit about me first. I'm Jonathan Martin. I'm an instructor and web developer with a consultancy in the US called Big Nerd Ranch, or if you prefer, Small Geek Vinaigrette. I've heard it both ways. We're based in Atlanta, Georgia in the US, and at Big Nerd Ranch, we develop web and mobile apps for our clients, and we teach other developers to do the same through our intensive 5-day boot camps or through our best-selling programming guides, which you can find on Amazon. So because I work with Big Nerd Ranch, I'm originally from Atlanta. But I've done a little bit of traveling lately. I've currently in Mobile, and then for a little bit I was in Dallas. So really nowadays, I work from anywhere, not any particular place. I can work from anywhere, and this is because I'm a digital nomad. So digital nomads are people who leverage technology to work from anywhere, and consequently, they tend to travel quite frequently. And there's a lot of really cool perks to being a digital nomad. I mean, instead of working from a space like this day to day, I might have a view of Italy's Amalfi Coast from my office on a given day. This is the kind of office I like. And so over the past 3 years, this nomadic lifestyle has allowed me to nurture my love for landscape photography. But the nomadic lifestyle didn't really come naturally to me at first, because there's a lot of interesting skills you have to be a digital nomad. You have to be really good at catching last-minute flight deals and living out of a tiny little backpack for a couple months at a time. So some interesting skill sets. Now, digital nomads come from a lot of different professions. For example, a lot of bloggers, journalists, developers, foodies, all travel around the world, and they enjoy the freedom that a digital nomadic lifestyle gives them. But despite the diversity of these different backgrounds and professions, all digital nomads tend to face some pretty similar situations. They're often collaborating with other colleagues on the go from just about anywhere, including places with either a poor internet connection or no internet connection at all. So really, hotel and McDonald's Wi-Fi is pretty much as good as Wi-Fi gets for a digital nomad. So digital nomads face these sorts of interesting challenges that aren't always solved by mainstream tools and applications that we might recommend to them. Well, so my personal interest at Big Nerd Ranch is creating software for digital nomads, for this interesting group of people who have these interesting technological requirements. So to dive into some of the different technical constraints we'll be dealing with, we're going to focus on two travelers. We have some really nice avatars up there, very memorable GitHub binary bit art. So these two people are Alex and Beth. Alex is a foodie. He's interested in food culture and trying cuisine from all over the world. And Beth is a travel journalist. And so Alex and Beth are traveling through Europe together, and they want to write a blog post about sandwiches. Just because. Well, they want to create this incredible expose on sandwich making as they travel through Europe. So what tools right now would we recommend to Alex and Beth so that they can write collaboratively on the go? Well, we're developers, so we might suggest a version control system like Git. Git is, after all, offline first, and it has advanced workflows for merging changes. So, yay Git. Until this. It's not exceptionally well suited to writing. Diffs tend to be line-oriented and generate a lot of noise. And yes, there is a word diff mode, but it doesn't work for patching, so you can't patch in one word at a time, so not so great. The interface isn't exactly memorable either, especially for people who don't tend to open the terminal on a daily basis. So, and the git commit workflow is also kind of untimely, so you're not going to have any real-time collaboration feedback unless you can really type git add and git commit and git push within a few milliseconds. So maybe Git isn't quite the best solution for our writers. So naturally, we might turn to something like Google Docs. Google Docs is sort of the holy grail in collaboration for on the go. So a lot of digital nomads, a lot of writers, a lot of bloggers might use a tool like Google Docs for this. And it works pretty well, especially if you have an internet connection. But if you don't have an internet connection, you'll probably be dealing with this. So Google Docs is not resilient to being offline for long spells. Even though there is an offline version of Google Docs, you're not exactly going to be able to continue collaborating. If you make changes for too long and you get back online, Google's simply going to tell you, I give up. I can't merge these changes. So Google Docs really isn't a great solution for the kinds of issues that frequent travelers and digital nomads might be facing when they want to collaborate on the go. Well, maybe let's take a nerdier approach. Maybe you've heard of Etherpad. After all, Alex and Beth, if they're traveling together, maybe they'll be close enough that they can create a little ad hoc network or use Bluetooth networking and then use something like Etherpad to collaborate over that networking connection. So that seems like it could work, except that unless you're a nerd, you've probably never heard of it, and writers probably don't want to be using a plain text editor. So Git, Etherpad, and Google Docs, neither one of those solutions quite seems to fit the use case of a digital nomad. If we really want to help Alex and Beth, we want to give them something that's offline resilient, that gives them real-time collaboration when they do have network connectivity, and have it all be seamless. You're kind of hard-pressed to find a product that does those sorts of things. Now, the good news is we actually already have the algorithms to create great software for digital nomads like Alex and Beth. So in this talk, we're going to investigate the 3 basic parts that you need to create a compelling collaborative experience for digital nomads or just any kind of creative industry where you're collaborating. So we're going to be discussing writers, but in fact, most of the techniques we look at are applicable to collaborative music. Maybe you have 2 people who want to collaborate on sheet music, or maybe they want to collaborate on sound recording. They can do that with these same algorithms. So the first part of this talk, we're just going to look at the algorithms behind conflict resolution. How do you let 2 or more people make changes to the same document at a time and then resolve those conflicts seamlessly? That's going to make up the bulk of this talk. And then, of course, we'll need some way to communicate those changes between peers. Some way to say, hey, I made a change. You should probably update your copy of the document. So we could either do that over the internet, or we could look at some different peer-to-peer technology that allows these computers to collaborate without being connected to the internet. And then finally, since they are writers, they probably want a really compelling editing experience. So we'll take a look at what web technology offers us in the way of compelling editing experiences. So let's start with the hardest part of this talk, and that is, how do we resolve conflicts when multiple users edit the same document simultaneously? Now, in web development, in development in general, we have a fundamental limit, and that is the speed of light is slow. So are routers. Routers make it even slower. Computers are slow. Now, relatively speaking, it's not that slow, but it turns out it adds up. And so for Alex and Beth to be able to make changes to the same document simultaneously, we can't force one to take turns. We can't force Beth to not touch the document while Alex adds a few characters here and there. That's simply not feasible when we're talking about peer-to-peer and real-time collaboration. So we need to look at some algorithms that allow Alex and Beth to make these changes simultaneously, but have an algorithm that can merge those changes without supervision. After all, we don't want to have them basically have the experience of doing git diffs and git merge. So we need an algorithm that can combine changes that were made at the same time, but does it in a very predictable way so that Alex and Beth always end up with exactly the same copy of the document. Now, this particular constraint is called strong eventual consistency. Now, if you've looked into different database paradigms, or maybe you're using something other than Postgres as your main database backend, you might be familiar with the BASE database paradigm. Normally, we think in terms of ACID, which always guarantees that whenever we query a database, that we're always getting the most recent data, and that if something's being written to it, that the database is going to be locked down until that write has finished. So certain constraints like that in the ACID framework. Well, in BASE, instead, we decide, okay, we're going to give up read consistency, but we're going to we're going to make sure that at the end of the day, once all these changes do get synced up, that everyone ends up with the exact same copy of the document. We typically call these replicas. So Alex and Beth, if they're both working on a document, we would say that Alex and Beth have their own replicas of the same document. And at the end of the day, once they communicate those changes with each other, they should end up with exactly the same copy without having to do a full resync. So this is eventual consistency, and it's one of the key constraints we need to build a real-time collaborative editor that works well when the network is poor, or in some cases when you don't have a network connection at all. So we're going to take a look at some different scenarios to see how we can help Alex and Beth. And so in the first one, Alex and Beth are hiking in the German Alps. And they decide, while they're hiking, they get a little hungry, and they decide they like to have a picnic. So they pass a market, so naturally they decide, hey, let's put together a grocery list, let's split ways, and just start getting the groceries. That way we can get this done in half the time. So initially, they put together this great-looking picnic: milk, bread, and eggs. So they go into the grocery store and they say, all right, we're just going to get these items, we'll go separate ways. While they've split up, however, Alex remembers, oh, you know what? I'd really like to grab some apples, and really, I'd rather not get bread. The bread here isn't all that good. So Alex decides to make a change to his grocery list. He decides to remove bread and add apples to his copy of the grocery list. Beth, on the other hand, is lactose intolerant, and so she takes milk away from the list. Now, when Alex and Beth get back together, we now have a question. How are they going to merge these two different copies of the grocery list so that they end up with the same grocery list? So there's a few naive strategies we could take. The easiest one would be, let's combine these two lists into a brand new one and just remove duplicates. In other words, we should have every item from each person's list. We call this the union strategy. Now, the union strategy is a valid strategy. It's eventually consistent because Alex and Beth only have to tell each other what items they added or removed, and they will end up with exactly the same copy of the document. So, in other words, union is eventually consistent. So it's a good algorithm in that case. But there's also another equally valid strategy. We could use the intersection strategy to only keep items that are common between both lists. So it's also eventually consistent. So which one do we pick? Well, neither of those strategies solve the fundamental question. If we go back to the list and we look at what happens to bread and apples, we'll see that Alex removed bread, he added apples, Beth removed milk. If we look at the union or the intersection strategy, neither of these solutions preserve Alex and Beth's intentions. If we look at the union strategy, we see that Alex was not able to remove bread like he had originally intended. He was able to add apples, however, and we also see that Beth was not able to remove milk. So this means that in the union strategy, one person can never remove an item. Both people have to simultaneously remove an item. And in the intersection strategy, we have the exact opposite problem. You can never add an item unless both people do it at the same time. So these strategies really are a little bit too naive. But the solution is right there in the way we described this problem. Maybe instead of relaying exactly our current version of the grocery list, or in other words, the final state of our grocery list, maybe instead we should just relay these changes, kind of like a Git diff. So in this case, we might describe these operations. We might say that Alex deleted bread, he added apples, and Beth removed milk. Well, when they sync up, all they need to do is combine their changes, not the final state, but they combine their changes together into a single list, and now we can apply these changes one after another in no particular order and end up at a solution which preserves both Alex's and Beth's intentions. This strategy is also eventually consistent, and just as importantly, it preserves user intentions for both Alex and Beth. So this is a usable strategy for resolving changes to a set or unordered list. Unordered lists are pretty easy to deal with. Things change a little bit when you step into the realm of ordered sequences, or an ordered list, or if you prefer, a string, maybe a text document. So in our next scenario, Alex and Beth have finished their grocery shopping, they've had their picnic, and now they're ready to start working on that blog, that expose about sandwiches from all over the world. Eventually, it's going to be this really great piece. You'll probably see it on Hacker News. But first, they start off with a very modest document, and that is they start off with just the word sandwich in the document. So if we were trying to think about some different ways that Alex and Beth could make changes to this document in isolation from each other, we might try this scenario. So let's say Alex and Beth both started off with this document. It said sandwich. Then they both lose internet connectivity for a little while, and during that time, Alex removes the letter D from his copy of the document. Beth adds a letter to her copy of the document. She inserts the letter H at index 5. Well, we could immediately revisit the concepts that we just saw in ordered sets. Maybe instead of relaying the final state, the final copy of the document, we could just relay those changes. So here's one way we might describe those changes. We might say that Alex deleted the letter D, which was at index 3. And then we might say that Beth inserted the letter H at index 5. So we could try that strategy before, where all we do is we combine these changes and we run them one after another in no particular order. So in this case, first we'll apply Alex's operation, we'll remove the letter D, and then we'll insert the letter H at index 5. Unfortunately, we end up with this very interesting permutation of sandwich, however you can pronounce that. That isn't quite what Beth had intended. We see that Alex's intention was preserved. He wanted to remove the D, and it's gone. But the H was supposed to come after the W. So it's not quite enough when you have order to just apply these operations one after another. We have to make changes to resolve this. So even though Alex and Beth performed these changes concurrently, which means they're basically doing it in isolation for all intents and purposes, they're applying these operations at the exact same time. But depending on whether we decided to apply Alex's operation first or Beth's first, we end up with different solutions. This violates eventual consistency. For this algorithm to work, it has to be eventually consistent. So the problem here is that we applied Beth's operation after Alex's, and Alex's operation shifted the state. So if we take a look at Alex's delete operation, as soon as we remove D, it effectively offsets all of the other letters there. So we have this offset now of -1, which means if we want to figure out what Beth's operation would look like had she performed it on Alex's copy of the document, we can't just insert the letter at 5. We need to subtract 1 from it to get a better index. Now we can run that, and now we end up with a much more satisfying misspelling of sandwich, sandwich. So this particular version of a text merging algorithm resolves those changes, and it did preserve user intention between both Alex and Beth, even though they had to be applied in different contexts. Now, in a nutshell, this is how operational transforms works. So if you've heard of Google Docs, if you've used Google Docs, or if you've used pretty much any collaborative experience, you're probably using operational transforms. And essentially, when changes are made concurrently, each client performs the changes in some predefined order, and then it transforms any concurrent operations so that they can be applied to a different copy of the document and still make sense. Now, for operational transforms to work, they have to satisfy 2 mathematical properties, which we call TP1 and TP2. TP1 is easy. It stands for transformation property. TP1 is essentially the problem we just looked at, and then there's a much more complex one called TP2. But we'll go back to TP1. TP1 is fairly straightforward. It's basically the problem we just solved. It says that when Alex and Beth make simultaneous edits to the same document and they exchange those changes with each other, we need to ensure that they end up at the same copy of the document. So here's a classic problem you would use to see if an operation or if a particular kind of operational transform was TP1 compliant. You might get something like this. You might say, okay, Alex, insert a letter at index 3, and Beth, delete a letter at index 2. And if this problem happens, if they end up with different copies of the document, like Alex ends up with AXC and Beth ends up with ACX, this algorithm doesn't work. So for an operational transform to be TP1 compliant, it has to avoid this problem. Well, the particular solution we looked at did fix that. So we should be good to go then. So the algorithm we just looked at is TP1 compliant. We kind of get a quantum jump when we get to TP2. TP2 is essentially a problem that says when you have 3 or more people collaborating, how do you deal with this? So this particular problem says, what would happen if you had Alex, Beth, and Chris collaborating on the same document, and Alex and Chris insert letters around the middle of the string, and Beth decides to remove that middle letter, which is sort of like a pivot, sort of like a reference point for Alex and Chris's operations. How do you make sure that all three of them end up at the exact same copy of the document? A more naive operational transform algorithm will end up with some people having AXYC and some with AYXC. This is a problem because it has to be eventually consistent. So TP2, much harder than TP1. If you can get TP1 and TP2 correct, it essentially means that your algorithm will work amongst multiple peers and all copies of the document will eventually be consistent. Unfortunately, for text documents, there are actually no correct transformation functions. Up until recently, there are, this is somewhat of a lie, but they're all fairly impractical. So for text documents, there are currently no correct transformation functions. So this means that operational transforms, at least for a text document, cannot be used to build a safe, decentralized collaborative editor. Or in other words, operational transforms cannot be used to create a multi-peer editor. Instead, you always have to have a central server, some sort of go-between that transforms operations between these different clients. Meet Google Docs. That's essentially what Google Docs is doing. So since operational transforms, at least the ones that we tend to use, only support two peers, Google acts like one of the peers, and then everyone else is essentially that second peer. So Google kind of acts like this go-between between all the peers, which is why you have to have an internet connection directly to Google. Unfortunately, this is slow. Maybe compared to using Git, it isn't that slow, but in a real-time scenario or when you have a slow network connection, sometimes there can be quite a bit of lag when you're typing. So it's slow, it's centralized, and it requires a constant connection to Google's server. So this means that you can't really work on a Google Doc with a few friends in, say, one room using Bluetooth networking. This is also, by the way, why Google Docs does not work well when you go offline for long spells, because it's really only meant to work between two peers, and it doesn't do a very good job at that. So Google Docs, the Google team did an amazing job. They shipped it. It was originally part of Wave and then it hit Google Docs. So really cool algorithm, but it also turns out it's kind of the lower rung of collaborative algorithms. We can actually do better. So now we're going to try to level up. We're going to take a look at some tricks that might help us solve that TP2 problem. In other words, having more than two peers collaborating directly with each other without a go-between. So two of the tricks we'll take a look at are called preconditions and tombstones. So first, I'm going to show you guys a little bit of notation. This notation is borrowed from set order notation. It's just a formal way to describe how things are ordered in a set. So if you think about it, if you were to see something like this, this says that the letter S must come before the letter A, must come before the letter N. You could also write this as the letter A must come after S, and the letter A must come before N. Really fancy terminology, it's just an ordering. So if we took our initial string, sandwich, we could write it out with this notation. So this notation is just saying that the letter S in this document comes before A, comes before N, etc. Now, if you have a background in computer science, you might recognize this as a partially ordered set, or a post set. And in this case, it's a post set with a total ordering, which just means there's no ambiguity in terms of which letter comes before which letter. So when three people go to make changes at the exact same time, say now we have Alex, Beth, and Chris, we're trying to see if this new algorithm will solve TP2 compliance, we might try starting with Chris's operation first. And so we see that, okay, he deletes the letter D, but notice that delete operation has a little bit more information than it did before. Instead of having an index or anything like that, it now has these preconditions on the left and right. It says, before you can apply this delete operation, check and make sure that there's a letter N somewhere to the left of me and that there's a letter W somewhere to the right of me. So to be able to apply this operation, these preconditions have to be fulfilled. Well, we do see the letter D and it's between the letters N and W. So we can easily apply Chris's operation, which deletes it. But now once we get to Alex's operation, we already can't get any further. It says to insert the letter Y so long as it goes between the letters D and W. But now that precondition on the left is no longer met. We just deleted the letter D, which was sort of a reference point. And now that it's gone, we can't actually apply Alex's operation anymore. And nor can we continue on to Beth's. So fundamentally, the issue here is that we lost information when we tried to resolve these conflicts. So maybe what if we didn't lose information? What if instead of deleting the letter D, we just marked it as deleted, but we kept a reference in memory to it? This is called a tombstone. It's basically just a reminder in memory that, hey, there used to be a letter D here, but it's gone now. But that means that operations that were applied concurrently can use that still as a reference point until they get a chance to catch up. So now if we leave that tombstone in there, we can attempt to apply Alex's operation. So we see, I want to insert the letter Y before D and after D and before W. The D isn't there yet, but at the time Alex made this change, there was a D there, so at least I know where it should go. And the same can be done for Beth. Now you'll notice in Beth's case, we could actually put the E in two different places because it's not the only letter between D and W. It's up to you how you decide to resolve that tie, so long as all clients resolve that tie in exactly the same way. And so then when we want to figure out what the final string is, we just hide the tombstones and we end up with the final string. So tombstones and preconditions are a useful trick that allow multiple peers to collaborate on the same document without a central server. So we're a little bit closer to multi-peer collaboration. There's one catch though. So we dealt with just one tombstone. We just deleted the letter D from the document. But let's say that you've been editing this document for quite some time. You might have a lot of tombstones, and these tombstones take up memory. Essentially, this means that even if you have a document that only has a few characters in it, the document might take many megabytes in memory just because it's got all of this all of this tombstone information from previous editing history. This is fundamentally one of the difficulties dealing with the tombstone strategy. It typically requires some sort of complex garbage collection strategy, and oftentimes those garbage collection strategies are much more complicated to implement than the original algorithm was in the first place. So it might work, and there are some implementations of it, but they're fairly difficult to understand, and they're not always practical. So can we do better? We've seen two algorithms. We've seen operational transforms, and then we've seen techniques that use preconditions and tombstones. We can do a little bit better. So now we get into a class of data types called CRDTs. CRDTs stands for conflict-free replicated data types, and they're not an algorithm. They're actually a data type, so kind of like a tree or a linked list. CRDTs are a data type that naturally resolve conflicts without any special resolution algorithm. So CRDTs are really cool. If you implement the data structure correctly, you automatically can handle multiple changes at the same time, and there's no such thing as a conflict. So they're really cool theoretically, and it turns out they're actually easier in many cases to implement for real. Now, there are a lot of different kinds of CRDTs out there. There's one for sets, like grocery lists. There's one for counters. Unfortunately, for a long time, there hasn't been a good one for ordered sequences, like text documents. So pretty much operational transforms was the only algorithm you could use to deal with text editing. That has changed. We're going to take a look in particular at probably one of the coolest algorithms that I've seen so far. It's called LSEQ, the linear sequence. All this means is it's an ordered list, so it could suit an ordered grocery list, it could sort, or it could work with a to-do list, or it could work with a text document where every entry is a character, or maybe every entry is a word. Depends on how you want to implement it. Now, the interesting thing about LSEQ compared to a lot of other text-based CRDTs is that it's actually fast. A lot of the text implementations of a CRDT tend to be very slow and memory usage gets very high, and it gets very onerous to make changes to that document. LSEQ is actually fast and memory efficient. And let's take a look at the reason why. We'll go back to our document here, which was just the string sandwich. Now on a computer, we have many different ways that we could represent this string in memory on a computer. The easiest way would just be to have an array of characters. So a bunch of bytes, one after the other, in memory. But in a lot of programs, we use tree structures to store data, like a binary tree. Tree structures have very useful properties in regards to performance and memory usage. Well, LSEQ is no exception. In the LSEQ CRDT data structure, we have a very special kind of exponential tree. This tree in particular has a root node, and it can have up to 10 branches. So the branch factor, if you're following me and digging back into your bag of exponential tree knowledge, has a branch factor of 10. Now, you can actually tune this. You can pick other branch factors, but for our situation, we're just going to pick 10. And each branch is labeled from 0 to 9. For now, 0 and 9 are just reserved. Those are set aside for some implementation details, but all the other branches can be used. And each subtree works the same way. You'll notice that these branches are labeled with some number between 0 and 9, and they're ordered from left to right. So to convert this tree to a string, you might ask yourself, okay, this tree looks really weird. How on earth do I turn this into a string? All you have to do is a depth-first traversal starting from the left. So in this case, we just go down the tree, and every time we touch a node, we print out that character, and we start with the left. So it's depth-first traversal, and eventually we end up with a string sandwich. So in memory, we don't represent the string as a text document or as an array of characters. We actually represent it as this tree structure, which will give us some really cool performance benefits later. Now, we'll notice in this particular tree, it has 3 levels. So to specify any particular node in this tree, we could actually point out the particular branches, the particular branch number, to point to a particular node. So if I wanted to point to the node D down there at the bottom, I could say, go down branch 3, then branch 7, then branch 7. And now you know how to find node D. Well, that sort of gave us a unique thing. It gave us an address. You might even call this an ID. Now, this ID has a lot of really special properties that make it work much better than operational transforms in particular. So this ID, you'll notice, can get arbitrarily deep. What this essentially means is that you never have to move things around in memory. You just keep inserting in between. So unlike an array of characters where to insert something, you have to offset everything after that character, with this data structure, you don't. You don't move things around, which gives us some other really interesting properties. So TLDR, the address is essentially the ID for this node. So if we want to talk about any changes we want to make in the document, we could talk about an insertion. So let's say that someone wants to insert the letter Y between 2 other branches, between these 2 other addresses. Now, if we looked these up, we'd see that these are the nodes for letters D and W. So this insert operation is going to return a brand new address for us. In other words, where we should add this new letter. So if we wanted to insert the letter Y, this algorithm is telling us, hey, you should add a new letter Y. You should add it at the address 3.7.9. Now, unfortunately, I'm going to have to skim over this, but actually the bulk of the paper, if you go read about the LSEQ algorithm, the bulk of the algorithm is actually about how do you pick these IDs when you have multiple choices. Because if you make bad choices, your tree gets very deep, which essentially means you lose the performance benefits of having it arranged like a tree structure. But depending on how the user edits the document, you can't really figure out which ID you should pick if you have several choices. So most of the paper is actually dedicated to proving a unique strategy that, regardless of the user's editing behavior, picks good IDs. In our case, we're going to wave our hands, and we're going to pretend that we came up with a great ID to start with. We only had 2 choices, after all. So to apply this to the tree, all we do is we go down the tree looking for 3, 7, and then we see 9. There's not a branch for that. Let's just add it. And that's all we do. And again, if we were to read this out as a string using depth-first traversal starting on the left, this now reads out as Sandy Witch. Now you'll notice, even though we performed a text insertion, we didn't move anything. We just added a branch. Now there are a few edge cases where it does cause you to move maybe 2 or 3 nodes, but in the general case, you don't end up moving anything in memory. This means that inserting into a tree and deleting from the tree is fast. Compared to a lot of other text algorithms that were CRDTs, these were very slow, and typically they didn't work well with the typical document you do in Google Docs. This algorithm, on the other hand, is very fast. But what if we have Alex and Beth again, and they're making changes at the same time? So let's say that Alex did an insert operation. He's inserting the letter Y at the address 3.7.9, and Beth is inserting the letter H at 3.8.2. And these changes were performed in isolation. So now that they're going to sync up, what do they have to do to resolve the conflict? They don't have to do anything. They just apply the operations. They don't even have to apply them in any particular order. And this is where that word commutative you might have heard of. So typically we talk about conflict-free replicated data types. You'll also hear another modifier where we call it commutative replicated data types. This just means that the order of operations doesn't matter if they happened concurrently. So a lot of CRDTs, including this one, have this really cool property that it doesn't matter if you insert the Y first or you insert the H first, you end up at the exact same copy of the document. And this is because those IDs never change, which means they're immutable, which also means that once you delete characters, let's suppose you wanted to delete that H, even though you no longer have a reference to that node in memory, if someone else was referencing that node, those IDs tell you where it used to be. So you don't even need a tombstone for it. So TLDR, LSEQ allows you to have very good memory performance because the tombstones don't need to exist. The IDs themselves tell you where that item used to be. So if we read this out to a string, we now get Sandy Huich. That's a lot easier than what we were doing with operational transforms. Now, the tree, of course, looks crazier than just doing our little offset by one trick, but this works for any number of peers. And it turns out it's very resilient for long offline spells. So the key takeaway with CRDTs is that conflict resolution is baked into the data type itself. So a lot of times in computer science, you'll hear about algorithms and data types being two different ways to solve the same kinds of problems. And this is a classic example of that. And it turns out the data type approach is very elegant. And it also works really, really well. So in particular, the LSEQ algorithm data type is very powerful for text documents. Unlike operational transforms, it doesn't require a central server. In other words, if you have 4 people working on a document, they don't need one peer translating operations between them. They can talk directly to each other in sort of a gossip style. So if you had 10 people on the top of a mountain without any internet connection, why not? It totally works. This algorithm also doesn't rely on any tombstones, as we saw, or complex garbage collection strategies, which are often the hardest part of implementing some of the tombstone-based algorithms. So in turn, this means that the size of an LSEQ tree grows very slowly. And because it's a tree structure, this generally means that when you apply an operation or, like, say, insert a letter or delete a letter, it happens in log n time. Because the tree structure means you can get to these different nodes in the tree much faster. So LSEQ, the very powerful algorithm, unfortunately, it's mostly hiding in an academic paper. There's one implementation of it I'm aware of, which is one that I've hacked on. This is a JavaScript implementation of it. It's a very interesting algorithm, and the implementation is very research paper-y, so it's probably not something you'll use in a production application. I do have a demo I'll be showing, however, to show you that, hey, it actually works, and it can work with multiple peers. Now, there's actually some really cool CRDT work that's been happening right now, just in the last year. A really exciting new CRDT came out. It actually came out the week or so before I first gave this talk, and it's a CRDT for JSON documents. So imagine having a tree structure that has the same constraints of a JSON and being able to automatically resolve changes and conflicts to it. So the JSON CRDT is really amazing for cases where you want the CRDT approach for maybe something that works more like a tree instead of a string. So some examples that come to mind, Redux state. Maybe you just want to auto-magically sync state between a couple React apps that are powered by Redux. You could throw a JSON CRDT at it. Or maybe you are dealing with a NoSQL database and you want to resolve conflicts in some of those objects. You could use that. Now, unfortunately, this is mostly hiding in a paper. This is version 2 of the paper. They massively revised the notation, which isn't any easier for me to read than it was the first time. There's a reference implementation in Scala, and there's this really great implementation in JavaScript, too. Not really. I really wish there was. In fact, I would love to implement this. I've banged my head on the paper notation for a couple months now. It's quite beyond me. So actually, if you're good with Scala or mathematical notation or Haskell, please come find me, because I would like nothing better than to work with you for over the next few days and hash out some sort of JavaScript implementation. Because what more natural place to be using peer-to-peer and collaborative stuff than in the browser, where we all have internet connections, or we're using WebRTC. So help me make this a reality. I would love to build this sort of thing. So now we've looked at some different algorithms for dealing with conflicts. So now we get to the second part of this talk, which is how do we communicate those changes? Now there's a lot of different strategies for dealing with this. Maybe if we have an internet connection, we don't even have to worry about that. But if we're talking about algorithms that work between multiple peers without a central server, we might as well talk about peer-to-peer networking. There's a lot of difficulty to doing peer-to-peer networking, and I am just barely scratching the surface because I only know the surface, because peer-to-peer networking is hard. You have to solve quite a few problems to deal with creating a reliable and secure peer-to-peer mesh network that just auto-magically works. In particular, these are 4 of the hardest problems you deal with creating a peer-to-peer network. So the first is, how do you create a good network topology, one that is fault tolerant? So if there are 10 people in a room and each laptop is going to connect to maybe 2 of its peers at most, how do you pick those peers in such a way that most people can get a message to everyone else in such a way that it's fault tolerant? That's a difficult problem. How do you discover those peers to begin with? So what's the discovery mechanism? How are you going to relay those messages in such a way that you won't hear echoes? Maybe the same message makes its way back to you a few times. How do you make sure that you haven't heard this message before? And then, of course, securing it. How do you make sure that this message is authentic and comes from someone you trust? So with network topology, let's suppose that Alex and Beth are up in the mountains and they have a lot of hiking friends with them, probably because they like sandwiches and they offered the rest of their picnic. And maybe Alex wants to send a message to Beth, and there was this one connection, but the connection's a little bit fuzzy. If that connection drops out, Alex now has no way to talk to Beth. That's not good. So there's an alternate network topology that if we had that, it would be much more resilient to problems. So now if any of these connections dropped along the way, there's a better chance that Alex will be able to get his messages through to Beth. And so for the most part, we can just assume that if Alex wants to send a message to Beth, that it eventually gets there somehow or another. And so then we can abstract away this networking layer. And we can just assume that, hey, if I want to send messages from Alex to Beth, the message will eventually get there and it's reliable and it's secure. All of this ought to be provided at the transport and networking level. Now, some of this should probably sound familiar because we're basically reinventing how the internet already works with routers. So the TCP/IP protocol has incredible fault tolerance. If any router goes down or if one of the connections gets clogged, TCP/IP can automatically detect that and pick alternate routes. It also handles things like throttling connection speed and resending packets that get dropped. So these are all things that ought to be handled at a networking level. It turns out it's just a little bit harder with peer-to-peer because instead of having routers that handle this sort of thing, now you're making everyone's computer a router. So thankfully, some other people have done the work of reinventing the internet for us. So you might be interested in checking out some of these different popular protocols, these different network transports, which give you reliable ways to send these messages in a peer-to-peer fashion. Scuttlebutt, Gossip, Hyperlog. There's even a binary library that you can pull in called libp2p that gives you a lot of these network layer tools that you can use. So there's a lot of really cool stuff out there. It's a little bit heady. Most of it's beyond me. So I just list it. It's a little bit easier than trying to explain how all the magic works. Any sufficiently difficult problem domain is indistinguishable from magic. Now, if you're interested in seeing some more peer-to-peer awesomeness, some different things you can do with that, there's this really great page. I spent a lot of time just diving through this, all kinds of cool demos, just showing you some of the cool problems you can solve with peer-to-peer algorithms and peer-to-peer networks. Now, the last component was Alex and Beth. If they're going to do this writing, they need a really great collaborative editor. And this is where the fun begins for front-end developers, creating this great experience so Alex and Beth can start collaborating on the go. So I'm just, to motivate this a little bit, I'll show you guys a demo that uses the LSEQ data structure. And in this case, I'm cheating because I'm going to be using MDNS under the hood just to get them connected. But this would theoretically work over any transport. So this is a rich markdown editing experience. It's powered by content editable in the browser. And as you would expect, it doesn't work. Probably because I started this a few hours ago. All right. Hello, sandwiches. So, hey, it's a markdown editor. Really exciting, right? But the point of this is to show you LSEQ is doing this in the background. And LSEQ is just very powerful for text documents. But now imagine you had 3 or 4 people working on this. Think about what kinds of experiences and problems you could solve with any collaborative approach. Maybe you're a musician. Maybe you're interested in how can 3 or 4 musicians collaborate on sheet music together. There's some really cool text languages out there like LilyPond that allow you to describe music in text. Perhaps you could wrap a collaborative editor around it. Or maybe you're interested in just replicating Redux state. You can pull the JSON CRDT and get these incredible collaborative experiences for free. There are a lot of really cool solutions out there and a lot of cool problems that you can apply CRDTs to. If you're interested in seeing the source code for that particular demo and some of the hacks that I did on the LSEQ code, you can check out this repository. I do have a fair amount of work. I haven't committed back to it because I just did a lot of hacking and I wasn't too sure I was ready to commit it yet. But between these sorts of algorithms and a lot of really exciting connectivity options that are coming out soon, there's a lot of really cool stuff you can do that has nothing to do with an internet connection. In particular, I'm really looking forward to LTE Direct. Imagine being able to do peer-to-peer mesh networking with people from miles away without a cell tower. There's a lot of really cool opportunities coming out and a lot of cool new standards coming out that would allow Alex and Beth to collaborate with a crowd of friends over any of these supported networking options. And since there's no central server and you don't need an internet connection, peers can just directly talk to each other. And this gets us all closer to making great collaborative experiences for digital nomads like Alex and Beth. Again, we focused on collaborating as a writer, but these same algorithms could be applied in music or to artists who want to collaborate anywhere with the digital nomad lifestyle. It's just that all these algorithms are hiding in academic papers, some light bedtime reading. So there's a lot of cool stuff out there, but unfortunately a lot of it is hiding. So if you're interested in tearing away some of the covers and helping me figure out, in particular, JSON CRDT, please find me, because that is one that has not proved to be light bedtime reading. Now, if you're interested just in things related to the digital nomad lifestyle or you like pretty pictures, feel free to check out my site, yellowscale.com, or you can find me on Twitter @Nibbler. Any questions?